Hello, this is Terry Kuzma here at Penn State University. And what we would like to do today is in our bottom-up manufacturing course, we would like to review some characterization techniques that are especially useful for bottom-up manufacturing or on that scale. So the three that we selected to review is tipped enhanced Raman spectroscopy, scanning helium ion microscope, and the magnetic resonance sub-nanometer imaging. So what we're going to do in part one is we'll look at the tipped enhanced Raman spec, and they refer to that as TERS often. We'll do that in lecture one. Then we'll take a break, and we'll come back and review the two other lectures, or the two other subjects in lecture number two. So as an introduction, this presentation will cover some unique characterization methods that could be employed to interrogate bottom-up materials. In some cases, we'll review a related conventional characterization method and then detail how this method is enhanced for special applications or how this method was enhanced itself to get better resolution or increased signal-to-noise ratio. So the first method under review uses light as an interrogating force. The second method actually uses ions, and interestingly, the third method uses magnetic displacement. So to fully understand these methods, we'll contrast other methods, we'll conceptually build models, we'll discuss the physics, such as the light scattering, the magnetic displacement, or the ion interaction, and then we'll build some conceptual models and then look at the methods and limitations of those particular applications. So the first one we're going to review is TERS. It's tipped enhanced Raman spectroscopy. It's a refined method of the surface enhanced Raman spec method. TERS is desirable for detailed molecular information because it offers a stronger signal than SERS. So the structure of the discussion will be, certainly we want to look at SERS because that's the parent technique. And like we said, it doesn't have the resolution that we need. So we're going to determine how we can take the SERS technology or physics and then make that more appropriate for nanomaterials. So we're going to understand the physics of light to the material interaction in regular SERS, and then we're going to discuss how TERS is an enhancement of the SERS technique. So let's take a overview, take a step back and see what we're doing with SERS. So let's look at this parent technique. SERS is a vibrational technique similar to acoustic interaction of a wine glass with a tuning fork. Using this analogy for Raman, this tuning fork is the indirect coupling of high frequency radiation, such as light, and the chemical bonds act as the wine glass to absorb and to shift the radiant energy. The radiant shift is then correlated to the chemical makeup. So basically we're doing the same thing. We're going to have, in some senses, we're going to elicit, as on the left-hand side here, we have the tuning forks, and on the right we have our material that's going to capture that energy from the resonance from our tuning fork on the left. So what we're going to do is instead of a tuning fork, we're going to replace that with a light signal. And then what we're going to do is we're going to look at the material. And the material we can model is these wine glasses that have a unique resonance. But the resonance itself does not absorb the light interaction. It actually scatters from it. So there's going to be two different types of scattering. There's going to be elastic, where the molecule does not absorb any of the or shift the energy from the initial laser. And then there's going to be inelastic, where there's going to be a shift in energy due to the interaction with the molecule. So it's important to state that Raman differs from infrared absorbance, such as FTIR. SERS is a reflection measurement. So SERS is very sensitive to chemical bond length, strength, stress, strain, and arrangement in the material. So it's very interesting that a lot of times just in analysis of materials, there's a foundational idea that we can look at a material and be able to predict its implications with the environment due to some table that discusses the material properties. But in essence, that might be incorrect, because that particular material might have seen some other interaction with the environment such as stress, strain, thermal shock, etc. So from the book value, the actual interaction of the material is going to change. So we have to not only know the book value, but we often empirically measure the material because we might have had a change in stress to strain due to the history of the material. So that's what this detection method, the SERS, is going to do for us. So SERS is often used to derive structural characterization information more than chemical analysis, and it's often used in many industries such as pharmaceutical quality control and materials such as nanotubes. So the systems themselves for a Raman spec system, they can be large and complex, but they can also be used for small and handheld instruments. So they could be used for drug detection, they could be used for explosive detection, they can be used for law enforcement, for other areas that we're looking for drugs or terrorism, etc. So they can look at with these handheld instruments to give a quick estimation. So this handheld shown on the right is actually very sophisticated, and it can actually determine the presence of mixed and contaminated chemicals, and it actually has an extensive substance library. And to note from this, we show this handheld instrument. Basically, it's going to use light for the interrogation. A lot of characterization equipment uses to minimize interaction of other non-ideal properties. They often use vacuum systems. So it's important to note that this test is not done in vacuum. It's done in the ambient, and the interrogative force is basically a known light source that comes from that unit. So that's a nice picture, and I think it tells a little bit of a story. Again, our point of this discussion is not SERS, but we're reviewing that now. Later, we're going to get into TERS, which is actually kind of like this handheld unit, but it's also going to incorporate, interestingly enough, the atomic force microscope. So it's going to mix this unit and the AFM roughly in some conceptual model to be able to do our work. So the Raman effect is relatively weak. And what the Raman effect is, what we're going to do is we shine light on a sample, a known light source, such as a laser, and basically there's scattering of this laser light within the matrix of the material. The scattering comes in two forms. The scattering can be elastic scattering, and the definition for elastic for us would be the laser light hits into a molecule, it's scattered, but it doesn't change the relative energy of the laser light. So it basically is just reflected. There's also inelastic scattering, and that's where this laser light actually interacts with the molecules, and then it is shifted due to the interaction of the molecules. So that light then is reflected, and it'll be certainly a lower, it could be an increased magnitude or a decreased magnitude from the incident laser light. But something important to note is that inelastic scattering occurs at something like 1 in a million, 1 in 10 million, compared to the original scattering light, which we're going to refer to the elastic scattering light as the Rayleigh band. And then the Stokes, we're going to define Stokes as the inelastic scattering. And again, the Stokes scattering is going to occur at a very less likelihood, statistically less likelihood than the Rayleigh signal. So again, let's define that. There are three major light peaks that are reflected from the sample laser interface, and these provide chemical bond information and stress information. The strongest radiation is the Rayleigh line. This is the radiation is elastic interaction of the laser and the bond. This line is often filtered out from, that should be from, I'm sorry, that's misspelled there, the signal to better analyze other interactions. Second, lower energy interaction denotes residual vibration energy, is known as Stokes scattering. This re-radiation has a lower frequency than the input signal. This is for the Stokes line. It is reflected wave that is derived from the adsorption of the laser to the vibrational modes in the sample. So vibrational energy of the chemical bond is deduced from measuring the difference between the frequency of the Rayleigh line and the Stokes line. This identifies the state of the bond. This state shows chemical bonds and the stress and strain on the sample. This information is collected as wave numbers, and these wave numbers provide a fingerprint of the material under test. Another spectral line is formed from the thermal excitation of the chemical bonds. This spectrum is known as the anti-Stokes lines. Because it's based on certainly the same chemical bonds that we were looking at in the Stokes line, it actually is a mirror image of that. This line has a higher frequency with reference of the Stokes line. So it's basically a mirror image of the Stokes line is the anti-Stokes line, and what this is going to show is a shift in the thermal energy of the re-radiation of the light source. So the anti-Stokes line has the same distance from the reference Rayleigh line as the Stokes line because it reports on the same bonds. The difference is that the anti-Stokes incorporates ambient thermal energy. Therefore, the anti-Stokes line mirrors the Stokes line and has a higher frequency with reference to the Rayleigh line. In a typical powdered substance, the intensity Raman scattering is roughly equal to 10 million times less than the intensity of the Rayleigh scattered light, and therefore very sensitive instrumentation is needed for Raman spectroscopy. This gives the rise for the needs of TERS, which we're going to discuss later. So again, what we're going to get from this interaction of the laser light to the sample is the Rayleigh light, and the Rayleigh light is the elastic scattering, and that's going to be our reference line. What we're also going to get from this interaction of light with the substance is we're going to get inelastic scattering, which is a change in the thermal energy due to the interaction, or we're going to see the interaction of the thermal energy and the laser, and those are going to be called the Stokes and anti-Stokes line. The difference between those is going to report on the energy of that particular bond. So this is, again, the inelastic and elastic scattering. So we first have the Rayleigh line, which is we're looking at the incident light. And what happens is the incident light is equal to the reflected scattered light. And then we have the Stokes scattering. And what we're going to see here is we input, again, our laser light shown here on the left. The interaction the material does is shifts that light. So we're looking at this distance. And this distance of shift from the zero state to this virtual, and then re-emitting back into the state here. This is an elevated state because this will actually contain the thermal energy from the interaction of the laser. And then the anti-Stokes line here is what we're going to do is actually elevate an already excited, thermally excited molecule into the virtual state. And then what we're going to do is go back down into the ground state. So we're going to define this as the anti-scattering line. And again, this is the center line, and then these are symmetrically, the Stokes and anti-Stokes lines are symmetrically broadened from the Rayleigh line. And that distance is actually going to give us the energy of the bond, and then from that we can conduce the bond. So this shows us schematically the down conversion of the Stokes line, or the up conversion shifts of the anti-Stokes line and the wavelength. This shows us what we're looking for. So if we would look at conventionally, this could be a look at a material such as CH bond type material, and what we're looking at is the different types of energy that can be absorbed, vibrational energy that can be absorbed in these modes with this particular molecule. So this is an asymmetric molecule, so our symmetric stretching or asymmetrical stretching. We can also have twisting, which is deformation out of the planes. We can have wagging of this particular molecule, or rocking, or scissoring. Again, these different modes, or these different vibrational modes, are going to take a different amount of energy. So based on that energy that we report at with the Stokes and anti-Stokes lines, we can determine what kind of bonds are available for what kind of chemistries would be able to elicit this type of energy. Therefore, it gives us the chemical information on the substrate. So again, this shows us this absorption is qualified as wave numbers. So we can compare these wave numbers after we do a measurement, and we can look at these wave numbers and compare them to a library that's stored in the computer, the operational computer of our SERS system, and then we can make a determination of what particular material would look like this. Again, so this gives us, in some senses, a fingerprint of a particular material. So the Raman spec systems, they could be handheld units, as we discussed before, or we could have more desktop systems, as shown in this picture here from Thermo Scientific. So these systems could potentially be modular, and the reason for their modularity is different sources are going to be more tuned for different spectrums of analysis. So we can take a look at so we have this base unit and the infrastructure provided by this and cost provided by this base unit, and then the emission source, etc. What we can do is change out that emission source to better match our estimation of a particular sample. So we can take a look at this. The thing that we're going to switch out is the laser, the pre-aligned laser. So a blue or green laser can be good for inorganic materials, and for materials such as carbon nanotubes and other carbon materials, and for surface enhanced Raman scattering. We can also have another unit, and I'm going to go back in the slides here with this woman is replacing right here. We can have another unit here that actually has the red or near infrared lasers, and these are good for fluorescence suppression. So if we were using, looking at samples that could have materials in there that were fluorescent or phosphorescent, we could use these particular wavelengths and minimize that interaction. And again, those interactions would be best described in Jablonski diagrams that we're not going to discuss within this presentation. But the Jablonski interaction is basically that we would be able to have some change in spin state, and what that would convey is a change in spin and a change in vibrational energy. And depending on whether we would make a singlet or a triplet, that would elicit fluorescence or phosphorescence within a material. And again, that's out of this particular presentation, but if you were interested in materials that were per se fluorescent, I think that I could steer you to looking at some analysis, or I could do it later on at some time and look at Jablonski diagrams and how that analysis would help us understand what happens with the interaction of light to materials that are per se fluorescent. And then there are also another subset of these interchangeable units that could provide an ultraviolet laser, and these would be especially useful for molecules such as protein, DNA, RNA, and fluorescence suppression. So when these use a corresponding filter and gratings, we can customize these characterization techniques to quickly integrate materials that certainly we have a history of, and we can determine that these are the most appropriate for their test. And again, that's going back to this previous slide. That's good because we can reuse the microscope, etc., the data analysis computer and whatnot, joystick kind of thing to control the sample on here. And basically what we're doing is changing this emission source to customize this system. So it's nice to have this modularity here, certainly as a cost reduction, and then we can tune it in some senses by replacing the laser interface depending on what particular application that we're interested in. So again, let me move on here. So what we have to look at is moving on from SERS and the basic physics of this particular interrogation technique. What do we get out of TERS, and what is TERS? Basically what TERS is, what it does is it merges SERS with AFM analysis. And the AFM analysis is going to provide two things for us. The AFM, what it's going to be able to do is we're going to be able to take a sharpened probe tip, and basically the radius of the tip in its sharpened mode is going to be on the approximate size of maybe 10 to 30 nanometers. And what this tip is going to act as, because it's gold coated, it's actually going to act as a plasmon. So what the plasmon is going to do for us, it's going to act as, in some senses, a tank circuit, a tuned circuit, and the light, which is very, as we recall in SERS, the inelastic collisions and the light emission from the inelastic collisions is often millions of times less than the Rayleigh light length, the Rayleigh signal. So what we're lacking in SERS is our magnitude of our inelastic collisions, our Stokes information. And basically what the plasmon is going to do is be able to capture this Stokes inelastic interaction and integrate it on the surface. The other thing that, interestingly, that the AFM is going to do for us is the AFM is going to be able to take this plasmon detector, this AFM tip, which you were going to refer to, at least conceptually in our mind, as a plasmon detector. What that's going to do is be able to take this signal and put it in close approximation with the material. And we all know that these E&M signals die out as certainly exponentially, maybe as a first approximation, 1 over r squared. So what this is going to be able to do is capture these weak signals and integrate these weak signals. So this TERS integrating an AFM along with the SERS solves most of the non-ideal properties of our apparent SERS technique. So TERS is intended to solve some intrinsic issues with SERS. SERS has limitations because the Stokes emission light is very small. This is reduced even further by the desire to interrogate small areas. The spot size or interrogation size of interest with SERS is greater than a few molecules. So what TERS is, it actually brings us down to a smaller spot size. It interrogates the smaller sample size. It brings us into close proximity so that we don't lose signal. And it also integrates the signal in the plasmon resonance so that we can actually build up a signal and get a better signal to noise ratio. So this is a very, in some senses as an engineer, I think this is a very eloquent solution to the problems. So given these issues and constraints, TERS offers an eloquent and difficult an eloquent solution to a difficult and physically difficult solution, difficult to achieve solution. An AFM is used to bring a sharpened probe tip in very close proximity to the sample. This is important because the electric field decreases as a function of 1 over r squared. So the sensor needs to be in very close proximity to the sample for a strong signal. And again, this is what AFMs are good at, so it'll bring us into that very close proximity. This is still a very soft signal, but fortunately the tip radius can become essentially a place to confine and integrate the plasmon resonance. So this allows the signal strength to be increased by orders of magnitude from a conventional SERS. So the Stokes signals can potentially have a resolution similar to an SERS Raman signal. This plasmon resonance enhances the strength of the laser material interaction. So reading the literature, certainly sometimes they report that these signals of the magnitude of these signals can be increased multiple times from what we would get with conventional SERS, and depending on particular I guess interrogation types, because even this TERS can be enhanced in different ways, but they can be replaced. I think the resolution that some people report is on the order of 1,000,000 times what we would see with SERS. So this schematic here shows from Princeton Instruments, shows the combined surface enhanced Raman spec with the AFM plasmon to reduce the areas and give us this increased analysis. So this shows us a report from this paper that when we bring the tip, as the tip is approached, we get certainly a tremendous increase in the intensity of the signal. And when this tip is retracted in, I guess we would consider the typical SERS mode. When we bring it into contact, what we're going to do is get that increased magnitude from the signal and the integration of the plasmon. So we're going to get this, what we show in the red line, our very increased signal here. So again, this tip-enhanced Raman is really eloquent and certainly used quite a bit for biological applications to interrogate materials such as block copolymers, proteins, and DNA. So this shows us monolayer DNA and how this can detect the different attributes of the DNA on the surface. So this shows us that, and this is from this tip-enhanced paper periodical down below. So again, that's our presentation here on TERS as an enhancement on the SERS characterization method. So what we're going to do in part 2, we're going to take a look at scanning helium microscope and magnetic resonance nanometer resolution imaging. I'd like to thank you for your attention, and we'll talk to you in the next presentation. Take care.